Ever faced a concept so vast it feels, well, infinite, so big you can't quite get your head around it? Today we're diving into a mathematical marvel that literally tames infinity, turns it into just a single point you can actually picture.
Yeah.
We're talking about the Riemann sphere. It's this really elegant idea from the 19th century, and it connects fields like geometry, complex analysis, even quantum physics. It gives us these surprising new insights. So where do we even start trying to grasp this taming of the infinite?
Well, it begins by thinking about something called the extended complex plane. You basically take all the complex numbers, that flat, infinite plane you already know, and you add just one special point. The point at infinity.
Hang on, just one. That feels wrong somehow. I mean, with the real number line, you've got positive infinity and negative infinity, right? Two ends.
That's a really common intuition, but it's key here. The real number line is one-dimensional. It has two distinct directions, two ends. But the complex plane is two-dimensional. So think about walking away from the center in any direction, straight up, diagonally, whatever. All those paths, no matter how far you go, they all converge towards the same single point at infinity. Topologically, it just has one end.
Okay, so the dimension changes things, and making it just one point, that helps somehow.
Exactly. It makes the mathematics much cleaner, actually. Things that used to be problems, like dividing by zero, well, now an expression like z divided by zero, as long as z isn't zero itself, becomes perfectly well-defined. It just equals infinity, that single point.
Right.
It smooths things out for function theory.
Okay, so conceptually, we've got this extended plane with its unique infinity point. But that still feels a bit abstract. How do we, visualize it? Can we make it concrete?
We absolutely can. And this is where a truly brilliant trick comes in. Stereographic projection. Imagine you have a sphere, say a unit sphere, just sitting on the complex plane. Let its south pole touch the origin, 0.
Okay, got the sphere sitting on the plane.
Now imagine a light source at the very top, the north pole of the sphere. For any point on the complex plane, you draw a straight line from that north pole through the point on the sphere's surface and see where it hits the plane down below. Or actually, the other way around is more common here. Project from the plane up to the sphere.
So points on the plane get mapped to points on the sphere surface.
Precisely. Every point on the plane corresponds to exactly one point on the sphere, except for the North Pole itself.
And what do you think the North Pole corresponds to?
Points really far away on the plane. Infinity.
Exactly. That North Pole is our point at infinity. All the infinitely distant points on the plane map right to that single spot.
That's neat. But is it just a nice picture, or does this projection do something mathematically special? Oh, it does something remarkable. First, the projection is conformal, which means it preserves angles locally. Tiny shapes on the plane look like scaled versions of the same tiny shapes on the sphere. No distortion of angles.
Okay, conformality, that's useful.
But here's the really mind-blowing part. It maps all straight lines and all circles from the complex plane onto circles on the sphere.
Wait, straight lines become circles too. How does that work?
Think about it. A straight line on the plane stretches out to infinity in both directions, right? When you project that line onto the sphere, it becomes a circle that goes through.
The North Pole, our point at infinity.
You got it. So from the sphere's perspective, a straight line is just a special kind of circle, one that passes through infinity. It unifies lines and circles beautifully.
Wow. Okay, so this sphere isn't just a visual aid. It sounds like it has some deep mathematical structure, like a unifying language.
It really is. It acts like a kind of Rosetta Stone in mathematics. Formally, we call it a complex manifold, or maybe more commonly, the complex projective line, written as math BBCE11. Its power comes from how it sort of completes the theory of complex functions. Take a simple function like, say, fz equals 1c.
Right, that blows up at z. Zero, a singularity.
On the standard plane, yes, it's problematic at 0. But think about it on the Riemann sphere. The point z0 on the plane maps to the south pole of the sphere. The function OZ1z maps the south pole, 0, to the north pole, infinity.
Right.
And what about the behavior at infinity? Well, infinity maps to the north pole, and one infinity is essentially 0, which maps to the south pole.
So the function just becomes a smooth map from the sphere back to itself, no more blow-ups.
Exactly. It transforms functions that look problematic or have singularities into these globally smooth, perfectly well-behaved transformations of the sphere onto itself. It tidies everything up.
That's incredibly elegant, taking something broken and making it whole, just by changing the viewpoint. But it sounds very theoretical, this 19th century idea. Does it actually show up anywhere practical, like in modern physics?
Oh, absolutely. This is where it gets really tangible and, frankly, quite fundamental. Its most direct and famous application is probably The Bloch sphere in quantum
The
mechanics.
Bloch sphere? I've heard of that. It represents quantum bits, right? Qubits?
That's the one. The surface of the Bloch sphere provides a geometric representation for the state of a single qubit, a two-level quantum system. Every single point on the sphere corresponds to a unique quantum state. The standard basis states, usually written as 0, arrow, and 1, are typically placed at the south and north poles, respectively.
So it's a direct mapping from this abstract sphere to quantum reality.
It is. And there's a crucial geometric relationship. Two quantum states are orthogonal, meaning they are fundamentally distinct, like heads and tails if and only if their corresponding points on the Bloch sphere are antipodal, diametrically opposite.
Wow. Opposite points mean orthogonal states. That gives a really intuitive picture for something quantum.
It does. And it's not just qubits. You also see the same mathematical structure, the same sphere, pop up in optics with the Poincare sphere, which describes the polarization states of light. And there's even something called the Majorana stellar representation, which uses points on the sphere to visualize more complex states or even optical beams. It's surprisingly versatile.
It's just amazing. A concept born from pure mathematics, trying to make sense of infinity and functions, ends up perfectly describing the state of quantum particles and light itself centuries later.
It really is a testament, I think, to how often this kind of mathematical elegance and structure turns out to mirror something deep about the physical universe. The Riemann sphere isn't just a clever trick. It reveals these underlying symmetries and connections, showing how the geometry of a simple sphere can capture something as fundamental as a quantum state.
It really makes you think, doesn't it? What other seemingly messy or infinite problems, maybe even ones we face in everyday life, could be radically simplified if we just found the right, elegant perspective. The right sphere, so to speak, something to ponder until our next deep dive.